And welcome to the IEEE IES Western Australia chapter May webinar. This is my great pleasure to have Dr. Remember Samu, Senior Power System Engineering, APD Engineering, and co-founder and CTO of the Next Century Power in our today's webinar. So I'll just briefly introduce, Remember, and later on I will invite him to, start his presentation. So Dr. Remember Samuel is an accomplished power system engineer with over a decade of expertise in analyzing, designing, and optimizing power system across both distribution and transition networks. He is a co-founder and chief technology officer of Next Century Power, where he focuses on delivering cost-effective and sustainable electrification solutions throughout Africa. Dr. Samu holds a bachelor in electrical and electronic engineering from Eastern Mediterranean University and master in sustainable environment and energy system from Middle East Technical University and a PhD in electrical engineering from Murdoch University. Without further ado, let's invite Remember to start his presentation. Remember, are you here?
Yes, I'm here.
Yes. Please share your screen and start your presentation. Thank you.
Okay, yeah. Thank you so much. Without wasting any time, I'll try share my screen. Okay. So all right. I don't know if you guys can see my screen.
Yes, I can see. Just change to the presenter mode. Thank you.
Yes. Okay, thank you. Righty. Okay. Sorry, it's sharing the wrong screen. I share this one. Again, it's the wrong screen. Okay, yeah, is that better?
Yeah, let's start.
Okay, yeah, thank you. So again, good afternoon, evening, morning, everybody, depending on where you are. Today, I'm going to give a talk about a research or part of my research, which was a collaboration between Murdoch University, Horizon Power, which is a utility company serving mostly remote areas of Western Australia, and together with a German solar research center called DLR. So this research is was collaborated by those three, and the topic will be development of a control strategy for islanded remote hybrid microgrids integrating nowcasting. So without wasting any time, I'll go straight into the sort of outline. What I'll try go through is just the background of this particular research and the problems or gaps that we sort of realized was we're doing sort of a background check of how this research can actually collaborate or contribute to the electricity, mainly the distribution electricity or remote hybrid microgrid space, where there is an increase in PV penetration, distributed PV penetration actually. So we'll go into the method that we sort of followed, which was a step-by-step or staged methodology for us to try and accomplish the final sort of goal of the research. So without wasting any time, I think basically here I'll go into the introduction straight away, where I won't waste more time, which is basically there has been an increase in PV penetration. This is just around the world, but looking at Australia, it's one of actually the leading sort of PV penetration, where we've got over a kilowatt per capita in terms of PV penetration levels. So now, looking into these high penetration levels in remote hybrid microgrids, they actually sort of it's a good thing, because this is against the increase, especially as you have seen in the past 2 years or so, where fuel prices have really gone up. Most of the remote hybrid microgrids or the remote microgrids were served by diesel generation, and this will just become explicitly expensive. So this is where there's been an increase in PV penetration levels, which is I can say a good thing, and probably a bad thing as well. I'll explain further what do I mean by that. So this introduction of high penetration of PVs is actually sort of introduced, which is not a new phenomena, but it just sort of solidified the need of what we call a microgrid. And these are becoming more and more sort of ways of generating electricity, rather than having a whole sort of network being extended from sort of a major capital city to all the way to a very remote area. This can be costly, or sometimes it's not so secure. So microgrids are really gaining attention. So I tried to do now a bit of research into just the definition, because microgrid itself has never been really defined, but combining a lot of definitions, I found that this is just another power system, only that this system is serving sort of a small, hence the word micro, small group of customers. So it's a grid on itself, because it has got generation probably with a small distribution system, and it's got the loading, which is the consumers basically. Now, the advantage is that these microgrids can either connect or disconnect from basically the main grid in case there's been need for that to happen. But in this particular research, we're now focused in those islanded microgrids. We are saying these are microgrids that are literally just not connected to the main grid, and they're sort of generating electricity within the vicinity of where the load or the customers are, and they are operating in a islanded mode. So this is what we are going to be sort of talking about in today's talk. Now, as we have seen that, okay, we are saying because we are not extending the bigger transmission system or extending the grid from a distance which is very far away to where we've got remote customers. So it is an advantage, because we are now saying a microgrid is not going to have all that transmission network. It's just us now utilizing local resources, meaning we are going to have our own solar being generated in the same sort of small area, and we're going to have our own network within where the load is needed. This, as we cannot argue, is actually leading to a reduction in greenhouse gas emissions. This has been a talk probably over the past 2 decades now. And of course, because we are saying we are minimizing the use of diesel, which has been more expensive, we are removing the transmission network itself. So there is actually a reduction in generation cost of electricity, hence also a reduction in the levelized cost of electricity, actually, the customers. But now the major problem is now the variability nature, or how some people might say it's intermittent, but the word variable will be better in the sense that at 1 minute we can have full-on solar being generated, and because this is distributed resources, we will have a lot of variabilities in the event. For example, let's say we've got a cloud passing an area, or passing an area where there's these distributed solar resources. This can cause a variable sort of generation of electricity. Now, so this is actually a problem in terms of actually the system strength itself, in terms of actually the control of the system our output itself, because by all means we want to have constant electricity being generated. So now this problem is what brought about basically this type of research that I'm sort of going to talk about today. Like, how can we try and mitigate the effects of this variability nature of this output of PV? How can we mitigate its effect, and how can we reduce the need of high spinning reserve? Because one way of sort of trying to minimize this effect of variability nature of PV is for us to be operating, if it's a remote hybrid microgrid, let's say it has got diesel generation and PV generation. At this point, let's say we exclude batteries. What will happen is that I will basically have to have a high spinning reserve for me to cater for the unknown drop in PV. So in this case, I'm going to have to run my diesel generators almost all the time at high spinning reserve. So an example of such an event where there was a lot of PV coming in and a cloud suddenly passed actually happened in the place of this study, where this study was mainly focused. It's a remote area in Western Australia, which is called Carnarvon. So this small video will capture what happened in one of the days actually in Carnarvon. So what we're seeing there, or what is happening there, is these are actually distributed solar sort of resources that are within the vicinity of this research. And at one point, we were having PV output generation fluctuating in this sense. So a cloud was literally passing over this area, and this happened in real time. And what we can see in the sort of top left corner, depending on your orientation of the screen, we can actually see a camera showing how the cloud was passing and how the cloud was passing through different PV systems, and the output of this being sort of shown at this point, where the power generation per watts in this distributed system was sort of being shown. Now, this is actually a problem, because if this is happening and I am sort of not capturing that effect, I'm not mitigating the effect of that on my system itself, then my system will either trip because I don't have enough generation, or at that point, my system at one point probably I will have more generation than what I need, because I'm not capturing that. All I need to do is probably end up curtailing a lot of PV output because I'm not sure of what's coming out. Now, to mitigate all those effects, now that's how I came about the problem that we faced. So the problem is that with this increased distributed system, there's a variability in the generation output. Now, this variability, for me sort of to cater, or how they're trying to cater for this variability right now, or trying to solve this, is either running a system with high spinning reserve. That is, at that point, you're just as much as you can, having probably more than a base load covered already, and limiting the PV output. So at that point, you are not utilizing full resources. If you look, if we're talking of real world scenario where this Horizon Power, again, this utility, what they were doing before then, they were actually having what they call hosting capacities. So this hosting capacity was basically a way of saying, this is only the amount that we can actually put in our system, right? So as of end of last year, they actually removed this capping of PV system and tried to sort of have ways of controlling as much PV that you can put without actually putting a cap on it, right? So this is the problem that we figured out. So now this research talk of today is to try and see if we can minimize the effects of this, and if we bring in a new sort of technology system, or a new system that will sort of have a control strategy that will not minimize the input, the penetration of PV, and at the same time, it will minimize the use of high spinning reserve, or the use of the diesel fuel that is maintaining lower spinning reserve. So a bit of literature where at this point probably I'll need to define what is nowcasting. The word nowcasting probably the one I'm showing at this point. Now, this nowcasting basically is a forecast of irradiance, solar irradiance, but this is a very short-term forecast, right? From a matter of seconds to 1 hour ahead. So this forecast, if I have this forecast, different literature, of course, I didn't present all the literature that we found here. They have got different forecast resolutions. So these forecast resolutions, probably if it's a day ahead forecast, that can be used in the market modeling and all that. If it's a 5 to 10 minute or 15-minute ahead forecast in distribution levels, this is very important. I can actually use this for rain rate control. We can use this for the control of spinning reserve as well, or having that spinning reserve strategy. So different forecasts can be used for different sort of uses. So now what I'm interested about is this very short-term forecast, and to see if I'm able to do this very short-term forecast, and if I can predict probably what is my output of my PV system, or what is the predicted output of the PV system in the next 5 minutes or in the next 3 minutes, then if, for example, I've predicted that I'm going to have a large drop of PV, large in the sense that there's a certain cap I would put. If I'm going to have a large drop, if 3 minutes says there's going to be so much drop, probably you need to turn on a generator, then I've got enough time for me to switch on the generator, and it will come to almost full generation in 3 minutes, right? Instead of me running this generator all the time, I'll just capture when it's needed, and of course switch off the generator when I actually predicted that it's not needed, or keep on the generator, or keep the generator off if it's not needed in the next 3 minutes. If the drop is so small, but again, I'm seeing that I'm going to have another increase in PV output in the next probably 5 minutes, so there's no point of actually switching off and on the generator. Probably I can just play around with the smoothing of my PV system output. So that was just the introduction of what is nowcasting. So looking into different sort of studies that they were done, most of them are in the Oceania region, where there is small microgrids around the islands, and some in here in Australia itself. This is something that they've tried to develop systems that do this nowcasting, but they were missing just probably the controllability, or they were missing that automation of controlling the PV output, or they were missing the real life scenario of trying to test this. By real life scenario, I'm saying using a real sort of network to actually test the system that they can develop. So this is what brought us to how I was sort of performed the method now. In this development, what we did first was to try and catch what are the thoughts of actually using nowcasting in actually trying to minimize nowcasting, to integrate it to microgrids and try to minimize the use of diesel fuel. So this survey was an international survey. It was an online survey that was sent to developers of nowcasting tools, researchers that are working in any form of solar PV or solar output forecasting, industrial by industry. I mean, we've got the developers of microgrids themselves, or the engineers who are working where microgrids are being, or remote microgrids are being operated. So this research was mostly, again, the participants were mostly from the Oceania region, and as well as other microgrids even within Africa, within the Mediterranean region, and also in Australia, just to get a feel of what do they think this type of study would bring, what are the advantages of this type of study, or can I actually use this type of technology to control microgrids. So that was the survey. What was that? That is the survey was trying to capture this. And the results of the survey actually came, and with a very good sort of response from the survey itself, we figured out that it was the benefits were outlined by different, of course. So I'll put as well later for those who are actually interested in the deeper results of the survey. They were published, so you'll find them as well if you want to go deeper. But just to capture what was important there, it was that if we actually use nowcasting in collaboration with even batteries, we can actually reduce the sizes of batteries we need. And this is actually very important because right now, as much as we are trying to design remote or to design microgrids that include batteries, the battery itself, the battery cost itself is still a bit high. So at this point, this was a benefit of actually using nowcasting or integrating nowcasting in the control of microgrids. The second one was actually we can actually reduce curtailment because by all means, we want to try and use as much solar generation or as much solar PV output or any amount of renewable output as we can without actually curtailing the output. So there was actually that possibility. These were benefits that were sort of expected or sort of came as a response from the survey. And we can actually reduce the fast ramps. As we know, the fast ramps or the reduction just from the video, we saw the increase and decrease of solar PV output. That's actually very, very that's actually very bad on the system strength itself or the stability of my system itself. So would want that to be a bit slower ramp, or I can actually ramp sort of down slower and sort of ramp up my generation from other resources like diesel and something if I'm using that as part of my mixture so that I have that smooth sort of exchange instead of having steeper ramps. And provision of stability. This was an advantage, but of course there were some challenges. The challenges are that in any as nowcasting is just like forecasting. So as with any forecast, there are actually errors that actually could be accompanying my forecast. So how to deal with those errors were some of the questions that came. Like this could be a challenge, and on an electricity network, on something important as electricity, the existence of errors could play actually a very big part in disrupting my electricity generation. Then, of course, this will be like an online system. It's gonna use network. It might be under security threat as well. Then there was the lack of demonstrated experience because this type of technology has not been harnessed, it has not been used, it has not been sort of probably used at an economical scale where we can have confidence in actually using it. So this is something that these sort of engineers or developers actually outlined, like, okay, we've had a bit of batteries for some time. This is new technology, so it will have that sort of resistance to actually using it before we actually prove its reliability, sort of. So that was one. And the system maintenance, both hardware and software, could be difficult, especially because we are saying this could be more important in a network that is islanded, and we want to try and minimize costs for those remote areas. Now, if I want to service the system itself, that could be a bit of a problem. So now, some of the ways to solve this was actually trying to validate this system, right, to just gain the confidence, and of course to collaborate between different industries, hybridization of techniques, and some forecasting. So what I did straight away after this was now to go and validate the system, right? So was to go and validate the system, because that was one of the gaps that was realized, that okay, the system is not validated, so because of that the system might not be acceptable to many parts. Now, after validating the system, so I could actually sort of develop the classes that I thought I would need to be able to control microgrids. then develop a control strategy now that sort of will be centralized and try to control all my distributed resources by using nowcasting. Then later I went into the way I would sort of develop what I call a dynamic PV curtailment, which I will not talk much here because it's a bit lengthy there. But of course, what I wanted to really capture was to say, okay, fine, there are going to be errors in my forecast, but how can I actually capture these errors in my control? Okay, then actually be able to run this on a realistic system that is a real network that is currently available. Can I actually put this sort of system developed technology, incorporate it in the real network, and see how this would affect my output? Okay, and yeah, all that would just be trying to answer the question that we raised basically in the questionnaire itself. So without wasting any time, went into the methodology itself, where we did a bit of literature. Then I did that survey. Then after the survey, what we did was to incorporate the literature and the survey and now develop which is the next part, where we'll actually go have the system, the nowcasting system, and do a trial of that system for the first time in the Southern Hemisphere, have that system run and try to see how it operates compared to other sites. It has been sort of evaluated, then incorporate it in my realistic microgrid and run and see the benefits. Basically, that was what we did. So to start with, this was what the system looked like. Our system had so it's called a nowcasting system. So nowcasting, like what I said, it's forecasting. It uses sky camera. So by sky camera, I'm just saying this is a sky-facing cameras. So these sky-facing cameras, of course, there's a bit of research and calculations that are done into the distance of the separation of the cameras and the number of cameras that you can use. In my case, I used 2 cameras. These cameras were sort of around 600-meter difference or separated apart that long. And all of them were logging into a server. So these cameras will log into a server every 10 seconds. It will log in new image, and I will have other sort of sensors to help with actually the forecast. So other sensors would be my pylometer for the direct normal irradiance, then direct horizontal irradiance, then global horizontal irradiance, all measured. And I also have some meteor data like the wind, as well as the wind speed, and as well measured to be able to put as inputs to my nowcasting system itself, right? So these cameras we try to put them away from any blockages, and they have to be raised as high up as they can, facing the sky, taking images. That's the first step. These images are being logged into data logger. Then I am sort of running, I'm running this whole inputs in a code that's developed. And this code, what it will do first is, for example, I can see on the top left corner, the first camera without any name is just an example of how the camera would be recording 24/7. And every 10 seconds, I'm getting images. So I'll get 2 images consequently, right, from those 2 cameras separated 600. So these cameras, for the interests of others, they're actually located at Murdoch University here in Western Australia. Now, once I generate those 2 images, I enter those 2 images into my software. So this software is actually sort of modeled. Everything is built in MATLAB, but it's a bit of a complicated MATLAB code. So I take those 2 images, put them there, and add the meteor data that I mentioned. Then from the first step I'll do is to have what I call 3D modeling of my sky. So I'll have my sky modeled first, and this sky would be modeled. Then the next thing is you would find the position of the cloud. So what I'm seeing there, the greenish sort of picture there, is how I would see the sky. So these 2 cameras, from that software I'm running, I would have a sort of a sheet which measures 8 kilometers by 8 kilometers. So this is the surface area I can cover with these 2 cameras. So I can see 8 kilometers by 8 kilometers, I can see my sky, I can see all the clouds. That's the first step. Then the dots that we are seeing there, the red sort of dots, that is where Murdoch University is. This is where the cameras are, actually. Okay. Now, we can see there's a gray patch just on top. This gray patch is actually, those are actually the clouds that I'm seeing. Okay. So now I can see the position of the clouds. What's left for me is now to continue taking those photos and predict at which direction are the clouds moving in. Now, at which direction are the clouds moving in, and at which speed are these clouds moving in? Now, I will generate what I call nowcast maps. Those will be the maps now. These maps, they measure 8 kilometers by 8 kilometers, but I'll be capturing every 20 meters by 20 centimeters box. I call that a box score space. Now, at that point, I can capture what is the irradiance at that particular box, 20 meters by 20 meters around the whole area. So this will actually help me if I just know the geographical location of my sort of PV systems. I can now predict what is the output of those PV systems, because these maps, I'll generate them every 30 seconds, but I'll generate 15 minutes ahead. So from that particular moment where I have the map 15 minutes into the future, I can generate the maps and see how they look like, because I've predicted the direction and speed of the cloud that I have. All right. So it means I keep on updating this every 30 seconds. My maps are generated. I update the speed cloud. I update the direction of the cloud. Then I update the output that I'm predicting on a certain particular geographical location. So this would sort of formulate where my starting point is. So if I know where my PV system is at, then I know how much cloud is coming, how much cloud is going to cover. Then I can predict how much output of PV is going to be there, basically, because this would sort of predict how much solar irradiance is going to arrive at that particular surface. Then using all those solar sort of models, I can predict the output depending on the module that I'm using. So this will be what those 20 meter by 20 meter boxes look like, 8 by 8 kilometers. That is the resolution. That is how much I can cover. Then I can look into the future 15 minutes ahead. Now, the question will be, why 15 minutes? It's because if you look at Western Australia, I'm looking at the height of my clouds, because that actually plays a part. You need to know the cloud base height. So the height of my clouds here, the clouds are a bit lower in Western Australia. Because of that, I can only see up to 15 minutes ahead. But if my clouds were a bit higher, or the certain type of clouds, then I can even see further into the future. But again, this actually comes back to the accuracy. So it means the more I go into the future, the less the accuracy becomes, basically, of my system. All right. So this first trial was to try and evaluate this system, the way it operates, and its accuracy. So from there, I developed these 3 classes now. What I just need probably for controlling a PV system in a real life scenario is to know whether the day is going to be clear, the day is going to be overcast, or the day is going to be intermittently cloudy. All right. So if it's partly cloudy or intermittently cloudy, if the day is going to be clear, then I use these other metrics. Again, there's a bit of a whole research that I did, a whole sort of publication that I did, and some metrics that I used for me to predict these 3 days first, just from looking at the irradiances. Then after I predict those 3 classes, what I'll do is now to see, because I was using the RMSD, or the root mean square deviation. These are actually metrics that I just use to check accuracy in any forecasting, basically. So just looking at this RMSD, looking at my particular system, the one I was looking at, right? If we look at the particular graph where my mouse is, where it says direct normal irradiance DNI results, if I look at my horizontal axis, this is looking into the lead time. So lead time 0, 1 up to 15 just means 1 minute ahead forecast, 2 minutes ahead as I go until 15 minutes ahead forecast. Then here I'm looking at the root mean square deviation, meaning the error in my, basically in my forecast, if the lead time increases. So what I'm looking at is now those 3 classes I developed. If you look at the class that has got the highest errors, is the intermittently cloudy class. which is sort of reasonable in the sense that intermittently cloudy, I'm saying it's very difficult to capture the errors if I've got a lot of fluctuations in my output, in my irradiance. But again, if I look at the 3-minute mark of that, it's not so bad, if I may say, because I can still use this, as I'll prove later. I can still use up to 3 minutes. The error is still okay to actually incorporate in my control strategy and still be able to find benefits out of it. Now, if you look at the one that has got the least errors is the overcast class. Overcast, where I'm saying my sky is literally overcast, there will be minimum errors in my forecast, which is meaningful. Now, we did a bit of a comparison because the other sort of research that has been done mostly by the DLR, the one I mentioned before, but they did this research in the Northern Hemisphere, right? In some other parts in the Northern Hemisphere, and they sort of developed and tried to do the same trial and check the accuracy of their system. Now, looking at the system that I had at Murdoch University, the accuracies are almost tallying and even performing better, if I may say, the one at Murdoch. But that being said, every location, because of its geographical locations and its proximity from the ocean, and as well as the cloud base height, that actually sort of changes the whole operation of this system. So we can say Murdoch was just a bit lucky, if I may say, in that sense. So the operation of the system was pretty much comparable, and because of that, we can say the system itself has been evaluated now. Okay, it can predict nowcasts. That is very good compared to other systems. Now, the next step was now to go into, so this conclusion was the system was good compared to other systems, it was comparable. Then for clear sky and overcast, I've got very low mean absolute deviation and root mean square deviations, and intermittent cloudy has got higher, which is as expected. And now these 3 classes that I developed, because you can even go, depending on what you want to use the system for, you can go into fine classification where you even have more than 3 classes. I had, like other systems, they had more than 8 classes because they were doing even more finer classification of these clouds types or irradiance types. So these 3 classes that I developed, they're comparable and they can be used in, that's all I need to know, whether it's overcast, it's got sunny, or it's intermittently cloudy, for me to actually run sort of my algorithm of controlling remote hybrid microgrids. Now casting system trial and evaluation came in place. At this point, we said, can I then, having this nowcasting, I've proved that the system is actually operable. It's operational, comparable to other systems. Now, if I've got distributed solar resources, right, and I've got a system with the diesel generators, can I then control centrally? So can I have like a central control to satisfy my load 100% of the times, but try to utilize as much PV as I can with minimal curtailment, because I know the future, and just be able to switch on my generators when I need them and reduce the spinning reserve. So this was now the next goal, trying to develop such a system. So how I did it was basically to say, I've got 3 possible scenarios that can come up. If I look at my system or my output of my PV at, for example, 12 p.m., and I want to look to sort of predict what would be my output at 12:03, 3 minutes after 12, 3 possibilities can be in place. One is I'm going to predict a higher output 3 minutes ahead. I'm going to predict a lower output 3 minutes ahead, or it's going to be equal. Okay, where equal might never be the case, but when I'm actually developing this algorithm or this control strategy, I need to have that system almost in place. So that was the whole scenario. If in 3 minutes ahead, I'm predicting a higher output, I would look at how high is this output compared to my load, the load that I want to satisfy. if this output being predicted together with my diesel is gonna be higher than my actually demand, then probably I need to switch off a diesel so I can still maximize the use of PV. So that was one scenario. The other scenario was if I'm going to predict less than what I can satisfy with my current mix, probably I'll need to switch on a generator if I don't have enough PV coming out in the next 3 minutes. Then I can actually switch on the generator now in time for the 3 minutes ahead. So these were basically the scenarios that would come up. And in designing this, first of all, like what I said, as of the issue that was raised by the survey participants, they said, what about the error in your system? Are you going to consider that error? So I did, because I calculated the errors in my system. Then I did the worst case scenario design where I would say, fine, without any error, probably the top graph would be my output, right? Would be my GHI, for example. But if I put an error, this is just in a sort of 10 hours of a day, around 7 a.m. to 5 p.m., right? With the error, this would have been my output. So I'm going to design my control strategy by incorporating the error. I would do without the error, then I'll still incorporate the error. Then I actually say, my system, is it going to be beneficial if still the worst case scenario is the case? Then I'll check what would be my output. So I actually considered these errors. I formulated some methodologies to actually incorporate these errors inside my sort of study. Then where I'm modeling this is actually a real system. So this system is actually a part of Carnival network. Of course, for some security reasons, some of the actual network street names, they're actually removed. But to just name it, we had 5 diesel generators, each of 1.6 megawatt. Then there were 3 PV systems. These 3 PV systems, they were modeled at 2.3 megawatts first, reason being, without any curtailment, this was the maximum that could be put in the current system with a constant load. At this point, this was a pointer which could be worked on further, where we can have variable load in that. Now, with that particular system, so how this existing sort of strategy would work, the existing strategy would just say, if it's intermittently cloudy, for example, we've got 3 generators that are on at this point, because I'm trying to cater for the cover of that particular cloud that's coming. I don't know how much it's going to cover, but I still need to satisfy my load. So I'm going to run 3 generators all the time, right? Depending on not knowing how much I'll lose. So I'll need to still cover for at the unknown drop in PV. Now with the developed strategy, I'm saying in time 1, I can see the cloud coming. I've used my generator, I've used everything, but because I know the direction of the cloud, I know how it's gonna get there and at what time. At this point, I can be happy to have 2 generators instead of 3 running until I know that in 3 minutes, in time number 2, the cloud would then cover this part of the PV, and then I can have now my generator, the 3rd generator on. That is this developed strategy. I can use 2 generators, then switch them, just switch on the generator in time if needed. So this would be the whole concept. I know the position of my cameras. Because of the position of my cameras, I can map my clouds, I can map my sky. Then having that mapping of the sky, I develop the direction and the speed of the cloud, then know how much they're gonna cover, and later know when to switch on or off. So this is just the basic operation of how this system would work. Now, into the results straight away. We saw that the first thing that we did, this was an example of an intermittent cloud, which I just produced here. Of course, I had all the other classes, different scenarios, but this is one scenario sort of to capture because it's more interesting to see what would happen then in my actual case where I've got variable output of my generation, right? What would it look like? So if you look at the graph where it says existing control strategy, adopting Mangala power station strategy, this is actually the power station where this strategy is currently. They were running between 2.3, right? Sorry, it was 1.6 to 3.2, 1.6 to 3.2 megawatt. That was the range of their spinning reserve strategy, right? So that their spinning reserve would keep to be up in that sense. Now, just to zoom into this particular output, if you look at the black line, which is basically the spinning reserve of the current strategy, it keeps to be up all the time because I don't know what time I would need to switch on or switch off my generator, so I'll have to keep it up. Now, on the developed strategy, I'll just tell you the developed strategy, the green one, where I said I'm not going to consider the error at that point. My spinning reserve is going to be lower, always lower than the generator. Now, always lower than the existing. Now, where my spinning reserve goes a little bit above the existing, if we look at the actual number of generators that will be on at that time, all right? So the second graph says loading and the number of generators. So number of generators that will be on at that time, I would have only 2 generators on, okay? I'll have only 2 generators on. The yellow line is actually where I'm saying these are actually the online generators without error consideration. So if you look at the yellow line and the green line on my left-hand side, the green line is the spinning reserve of the developed strategy, and the yellow line is basically the number of generators that I'll need. So the generators are mostly 2 of them, then maximum of 3 at one point, then get back to 2. So when I go on the lower number of generators, then my spinning reserve at that point will be higher. That means my generators are actually loaded better, and actually this improves the operation of my generators basically, right? Now, if you look at the black line, right, the black line on my left-hand side is actually the spinning reserve of the existing strategy. If you look at now the number of online generators of the existing strategy, at this point, there were 3 generators throughout. So no matter how my PV is going to increase or decrease, I needed to have 3 generators running throughout for me to satisfy, or for me, because at this point, I don't know how much I'm going to drop, PV I'm going to drop. So I need to keep them on. So this was just an example of how actually this system did improve the operation, because we're saying even better loading of a generator would mean better operation of a generator. You don't want the generators to be really underloaded, right? Then at that time, we actually checked the curtailment part, because I had to just develop that scenario where I would say, okay, fine, let's say I have got a lot of PV now coming in, then probably I would need to curtail at one point. If I develop this dynamic curtailment, which takes into consideration now capacity as well, how much PV will I curtail compared to like a constant curtailment that will be sort of just sort of subjected when you say, if this much PV comes in, then I'm going to curtail at this rate for these minutes. Normally, that's how it's operational right now. So still at this point, I saw the advantages that I would curtail a lot if I'm using the existing strategy, but with my my developed strategy, compared to the output of the real output of PV, my developed strategy would sort of follow that suit and just minimize the curtailment, meaning I'm using more PV in my system. Now, just looking into the advantages now that came up, just a few pointers. There were fuel savings in both my systems, about 14% fuel saving compared to the existing strategy. Then as well, curtailment was very, very reduced compared to the existing strategy. So the percentage is the number that I would want to catch. I would be more interested in the value-wise, because this could be any system. Like what I said, this system now, because of its operational here, it could be modeled anyway, where we've got the same sort of setting of a remote hybrid microgrid. So I'll just go into the percentage saving here. So about 14% of fuel was saved in just one day. This is a fuel saving, daily fuel saving, by the way. This is just 24 hours of saving, because I'll just say my system would go to the existing sort of strategy way of operation at nighttime, but when daytime comes, I switch to this particular type of configuration. Then, of course, more results would come into different sort of classes. Depending on the type of class, you would see different savings. So I just mentioned the intermittently cloudy because these are the ones I sort of did a bit of presentation here. But all the classes were sort of determined, and there were still savings in all classes, basically, right? And as we see on the overcast class, there was no curtailment. This is expected because I don't expect to have a lot of PV being generated, but still there were fuel savings compared to the existing strategy. Now, this being said, we identified that if we can trial this system outside other place, or if we can trial this system further away or to gain confidence in its operational, we can actually incorporate it in remote hybrid microgrids. Then this system was successfully developed, and as well, it was successfully integrated into a real microgrid. So we actually saw its operational in a real microgrid setting and its benefits in terms of fuel savings as well. So because we were able to actually do this in a realistic microgrid, this particular study or this particular research can actually be transferable to any other remote microgrid that has got the same configuration. So these were the conclusions that we figured out, and the contribution to the research could be further determined in the part of the publications that were published. But again, just to acknowledge that this was a research that was between DLR and Horizon Power, Murdoch University, together with some other co-supervised students that I work with. And these are some of the authored and co-authored publications within that sort of period of this research. And just to say, it comes as well as an ARENA-funded project that came to fund this type of research as well. And yes, I would sort of thank you so much. And for those who would want to read more or reach out, those are some of the publications and some of the contacts for the publication people. Thank you so much.
Thank you very much, Remember, for your very insightful and interesting presentation. It's time for our audience to ask their questions. Please feel free to ask your questions, if there is any.
Yeah, Amir, I start. Thank you, Remember, for your valuable presentation. A quick question. Is that your research, is there any plan to implement it in any microgrid? I mean, how practical is that? I mean, rather than, I guess you had it at Murdoch University, but what about any microgrid within Australia? Is there any plan to implement that?
Yeah, thank you so much, Moed. Yes, so like what I mentioned, this was part actually of the distributed energy resource trials for Horizon Power. So Horizon Power, my understanding is that, of course, they needed to know the real output of their trials and see if they can actually implement this, because they are trying to actually implement this down there up there in Carnarvon. So that could be one way of going it. And this, just to sort of mention here, it's still in very infancy stage, but I'm trying to actually implement something like this to see if it can actually benefit some of my own projects within my company back in Africa, to just see if this could be, because we are looking into batteries too much into it, but as a pilot project, can something like this be implemented, because all of them are just microgrids that I'm working with right now.
Great, thank you.
Yeah.
Thank you, Mayet. Thank you, Remember. Is there any more question? Remember, just one question from my side as a matter of curiosity. So is there any room for your research to further, integrate with the advances in the AI we are currently experiencing?
thank you so much for that question. I was actually expecting it. Yeah, because the reason why I said I was actually expecting it, because I think I see a bit of integration between AI into anything that is going to be internet related.
Yeah.
As long as something is going to be internet related, then AI is going to play a part even when it comes to even improving the forecast itself. I feel like AI is gonna real come in real better there, and to because all these sort of models that we developed here, they, as much as they are dynamic, they are not as fast as probably we need to capture them to actually have all the advantages that we can get. So in that sense, AI can really be a way, to be honest, to improve on everything, on the modeling part and on the forecast, especially the forecast part of this particular system.
Fantastic. Thank you very much for your comprehensive response. Is there any other question? Okay, it seems that I was the last one. Thanks again, remember, and thanks everybody for attending this webinar. Wish you all the best and hoping to see you in the next one. Thank you.
Sure. Thank you so much.
Thank you.
Thank you.
Bye.